Hi, in this exercise we're concerned with the Hund's rule and we're going to apply it to erbium ions, and we're going to use the rule in order to estimate what the effective Bohr magneton is. And the effective Bohr magneton is basically the total angular momentum for the erbium atom, right, divided by the Bohr magneton. So the number of Bohr magnetons that adds up to the full magnetic moment of the erbium atom. And the size of that. And in order to do that, we basically use the fact that the effective Bohr magneton is this G factor times this expression here, where J is the total angular momentum quantum number, and G is defined as you can see here in this as this expression, which can be determined in any quantum mechanics course. And basically, if we use this expression here, what's left to determine is this L, S, and J, right? The total spin angular momentum, the total angular momentum, and the total angular momentum, including L and S, right? And in order to do that, we notice that erbium has an electronic configuration, which is basically 4f12 6s2, right? And if we then take account that we actually have an ion in this case, which has 3 electrons less than erbium atom, we get that the electronic configuration of our ion is 4f11. And we're going to use this fact and use the Hund's rule, right? So basically, we'll schematically put out how to fill this F shell. The F shell has basically 14 positions, right? 7 for each spin, and you have 7 possible quantum numbers for angular momentum, ranging from -3 to +3, and then the spin quantum number could be either half or -half. And the Hund's rule says that you will fill these shells first by maximizing the total spin angular momentum. That means that we put all the atoms in the positive the positive value for the spin quantum number. That includes the 7 atoms with spin up here. And then we do that. We continue by filling the other shells by maximizing the orbital angular momentum L. And you see here that we fill up from the positive value, so we get the positive value for the orbital angular momentum. Then basically the third rule is that then the J, the total angular momentum, is if it is more than half filled, then you take the sum of the spin angular momentum and orbital angular momentum. And if it's less than half filled, then you basically take the absolute value of the difference between them. And we'll use this now then to calculate what these values are. So basically the total spin angular momentum is 7 times a half, right? And then -4 times a half, which is 3 halves. And for the total orbital angular momentum, we just sum up these ones because this cancel out. Right, so we sum up these ones, and that gives us 6. And as you can see here, 11 out of the 14 positions or possible states in the F shell are filled, so it's more than half filled. And then Hund's rule says that we should sum the two in order to get J. And doing that, we get 15/2, right, or 15 halves. And then basically we can use these relations and put in the relations we used before. Right, I can show you once more. You can use these relations here in order to calculate what the effective Bohr magneton is. And you can try to do this at home, and the result that follows is that the effective Bohr magneton is 9. Hello. So in this exercise, we're going to look at the Hamiltonian for magnetic contribution in a material, right? And in CGS units, the Hamiltonian is described like this, where you have this term and this term, right? And now we wonder which term is the paramagnetic contribution and which term is the diamagnetic contribution. And for B, we ask what is the Hamiltonian in SI units. So, well, the definition of a diamagnetic contribution is basically that it's opposite. The magnetic contribution from a diamagnetic term here should be opposite to the magnetic field. And the magnetic moment here is the negative of the energy with derivative of energy with respect to the magnetic field, right? And putting that in for the Hamiltonian, we can see that this term down here should get this relation here, that the magnetic moment is the negative of B, right? Because of that minus sign here. You get this relation. Basically, we say that the second term, used to derive the magnetic moment, will give a magnetic moment which is opposite to the magnetic field. And therefore, this must be a diamagnetic contribution, right? And this is the paramagnetic contribution. And we can see it's the paramagnetic contribution is constant. It's independent of the magnetic field. And let's take it down. For the second question, we would like to transform this Hamiltonian from CGS units to SI units. And we use these three translations, right? The electric charge transforms like this, from CGS to SI. The magnetic field transforms according to this. And C is basically 1 over the square root of epsilon naught mu naught, right? And we can see there, if you put these together and put EB over C, it transforms according to this, right, as EB. So EB over C transforms to EB. And you see that this term here, or this factor, is actually in our starting Hamiltonian, as we can see here. So you have EB over E divided by C, and we have EB divided by C, right? So we know that basically the C's here will disappear for our second questions. That's the only change, and thus you have this Hamiltonian in SI units, right? You remove the C, and that's basically the answer to that question. Hey again. So in this exercise, we're going to look at two paramagnetic contributions to the susceptibility in a cesium atom. And basically, the information is that cesium is an FCC metal, right? Or a CC material. And you have this lattice parameter, A. And also, let's assume that cesium contributes with 3 electrons to the free electron gas in the metal, right? So the question is basically, so what are the two paramagnetic contributions to the susceptibility in this material? And also determine the susceptibility at 300 Kelvin and compare how much each of these contributions that we had contributes to that, right? Okay, in order to do that, we first look at the F shell, where basically you have two contributions, right? One from the F shell, because you have an uneven number of electrons in the F shells still. And also you have free electrons that contribute. So all electrons that move freely in the material will basically couple to the magnetic field and give a paramagnetic contribution, right? And basically from the F shell you see that a cesium atom leaving 3 electrons to the electron gas will have ionic atoms left, right? And ionic left atoms will have this configuration. And this configuration basically has S equal a half, right? L equals 3 and J equals, since it's less than half filled, it will be L minus S, which is 5 halves. And putting that in, you get a paramagnetic, the effective number of Bohr magnetons, P, equal to 2.54, which we will need later, right? And we'll put this down here. Okay. So that's the contribution from the F shell. And well, that's basically how the Bohr magnetons, the contribution from the F shell, the actual susceptibility is equal to the Curie constant divided by the temperature, right? And the Curie constant can be determined according to this, where the Bohr magneton appears. And basically putting in the values, where N over V here is given, since number of basically N over V is 4 divided by A cubed, right? 4 atoms per cubic cell, and the units, as we saw, was A, right? So you put in the values for that, and the temperature in this case was 300 Kelvin, right? And you put in values for that, you get the magnetic susceptibility at 1.63 to the 10 to the minus 3. Right. And then we're going to look at the contributions from the free electrons. And the contribution from the free electron can be derived as such, as you have this factor times basically the density of states here, right? And using that the density of states here can be derived as basically 3 large N divided by 2 and the Fermi energy, where the large N is basically C times N. That's the number of contributing electrons, right? And C was equal to 3. We knew that. And also the Fermi energy can be determined just by using this approximation that you have electrons, the metal basically. Well, electrons are free in a metal, right? The free electron gas, free electron model. And by using that, you get this relation here, with Z is still the number of electrons contributing. And putting that in this relation gives you the susceptibility for the free part, which is 1 to the 23, 10 to the minus 5. And as you see, basically, since this is 2 order of magnitudes less than the susceptibility coming from the F shell, we'll basically answer that the magnetic susceptibility for this particular metal is 1.63 to the 10 to the minus 3. Hi, in this exercise we're going to look at the magnetization of a 3-level system. The system is a system where you, in the first case, don't apply any magnetic field, and then if you apply magnetic field, you get a splitting into 3 levels. And the energies for the 3 levels you can see here. And we also will, by using a substitution of variable, x equals this relation here, or this expression, we want to find an expression in terms of x of the magnetization, and also determine what the magnetization is in the low limit for x and in the high limit for x. Okay? And in order to do that, we use statistical mechanics or statistical physics, and in that case we get the number of atoms or the number of particles in a certain state divided by the total number of particles is equal to this expression here. And this is just this canonical c variable function, and this is an exponential of the energy divided by kBt, right? So we have this expression which is known to you. And here also you see that the Ni is just the number of particles in this, with energies EI. Okay, so these ones in terms of x for different i's, I 1, 2, and 3, are denoted like this. And from this we can then determine what the magnetization is. The magnetization is simply the sum of the particles in a certain state times the magnetic moment for the particles in that state. And the magnetic moment is minus the derivative of the energies with respect to B. And thus, if we take this sum, the derivative with respect to B is, for the different cases, is 2 mu B, 0, and minus 2b for the different cases, right? The first, the derivative is actually minus in the first case, and if the minus sign in front of the derivative gives you a positive sign, and the reverse is correct for this one. And if you just put in the values for the n here, you see that this expression becomes this here, where I just calculated what the sum is, and so forth. And so basically this is the expression for the magnetization in terms of x. Now, if you go in the low limit for x, you can Taylor expand the expression, and you will finally get the value 8 mu b times, so this is how I do the Taylor expansion here. I replace it by the two first term in the exponential, and then I cancel out, and you get this value, right, in terms of x. And for the second case, where an x is much larger than 1, you get that the magnetization is simply this, where the exponential with negative exponents become very small, and also the 1 here will become very small compared to these ones, and means basically that this expression here goes to 1, and simply you get 2 times the mu b times n here. So that's the answer to this.